Kia ora and welcome to video 2 in the series Delightful Differentiation. Today's problem is ramping up a little bit. Problem 1 was reasonably easy, this one's definitely harder. We have some function that we need to prove satisfies this differential equation. If you've done integration, the standard integration if you're an NCEA student, you'll know that there's maths out there that enables you to solve differential equations, but at NCEA level it's just separable differential equations that you deal with. None of the differential equations that look like this, that would be university maths. However, we don't need to solve this differential equation because we've already got the solution. We just need to prove or verify that this does solve that differential equation, so it's actually a differentiation problem. All the best, and we'll catch you after the intro music.
Okay, so we need to show that this solution here works in the differential equation, and to do that we need to differentiate it twice, chuck it in there, differentiate it once, chuck it in there, just put the function in there, and then show that all of it equals 0. Now that might seem quite straightforward, but for this particular function, if we differentiate it, we're going to need the quotient rule, which blows up because it's f dash g minus g dash f all over g squared. And then we're going to have to differentiate it again, which is going to blow up even more. So to do this, there's got to be a quicker way of doing it. My first attack was to do just as I've mentioned and use the quotient rule. However, a former student of mine who featured in a previous series did this question as an assignment and showed me the quick way, taught me the ropes, so to speak. So actually, you bring the x to the n up first. You get rid of the fraction. I mean, common sense now, always in hindsight, fractions make derivatives messy. So if you can move the x to the n up the top left first, and then use implicit differentiation. If you haven't got your head around implicit differentiation, maybe watch the first video on the series before we do this problem, which is definitely harder. So we differentiate this equation actually as it is. So the left-hand side is a product of two things. The f part, this would be the f part here, and that's the g part. So we have f dash g. N is a constant, so we can use the power rule for this. N x to the n minus 1 multiplied by g, which in this case is just y, plus the derivative of g times f. Derivative of g is dy dx, or y dash if you prefer that notation, although I'm going to use the same notation as the question, multiplied by f. Okay, so that's the product rule in action. The right hand side, well, cosine differentiates to minus sign, so we get minus a. We need an m in there, the chain rule, times sine of mx. And then sine, well, that differentiates to cosine, so we need plus bm multiplied by cosine of mx. Okay, what I'm doing there is an application of chain rule. The inner function is mx. I need to multiply by its derivative. When I differentiate a composite function, I always times by the inner derivative. The constants out the front, the a and the b, do nothing, but the outside function, cosine, and the for the second term sine, well, they differentiate to negative, the opposite of one another. Which means if I differentiate again, I'm going to get kind of back to where I start. And the fact I started with cosine plus sine, then I went negative sine plus cosine. I'm going to differentiate again and get the negative of what I started with, well, except for the constants in front, of course. Okay, one more derivative, because we need the second derivative in here. Okay, so differentiating again, the first term is also a product. The n in the front, well, we can just leave it there because it's just going to multiply the derivative by the same value. And how about I use a different color this time? That is the f this time, and that is the g for the first term. So n multiplied by f dash g. F dash is n minus 1 times x to the n minus 2 times y. And then g dash f. G dash is dy dx, and f is x to the n minus 1, and all of that's got an n in the front of it. And then we move on to the next term. The next term, now this is the f and this is the g. So if I differentiate the product rule, I'm going to get f dash, which is the second derivative, if the f is the first derivative. So d squared y over dx squared multiplied by x to the n, and then g dash f, n times x to the n minus 1 multiplied by dy dx. Okay, it's getting really messy. And on the right hand side, as I was saying, sine differentiates to cosine. So we get negative am squared cosine mx. Again, the chain rule, so we get an extra m. And cosine differentiates to minus sine, so we get minus bm squared multiplied by sine of mx. And then we have a look at how that compares to what we started with. A cosine mx plus b sine mx, and now we're at negative am squared cosine mx minus bm squared sine of mx. So we've got negative m squared multiplied by what we started with, which is x to the ny. So that's the trick in this. To simplify, negative m squared multiplied by x to the ny. Okay, now where are we heading with this? We need to make everything equal to 0, and we need to isolate the d squared y over dx squared term on its own. It doesn't have any coefficients there. It's just on its own. So if we look at just rearranging this equation a little bit by writing the d squared y over dx squared term first. Okay, that's that term there. I'm going to write that first. It's the only term that's got a second derivative in it. Then I'll group the dy dx term next. Okay, the second term, 2n over x dy dx. So it's kind of like when you deal with a quadratic. You put all the x squareds term together, then you put all the linear terms, and then you put the constant last. So where have we got dy dx? We've got it in there, and we've got it there. So if I group those terms together, bearing in mind that that first one has got an n out the front, and the second one has got n x to the n minus 1 too. So both of them together makes 2nx to the n minus 1, all multiplied by dy dx. And then lastly, I need to group the y terms together, bearing in mind that I want the right hand side to be 0, so this dude here is going to go to the left. Okay, what terms have I got left? I've got this one here, which has got a y in it, extra n in the front as well. So I've got plus n lots of n minus 1 x to the n minus 2 plus m squared x to the n all times by y. So I moved that right term to the left to make it a plus, and then I factored out the y because both of the terms had a y, equals 0. What have I done? Let's just reflect on this before we get the answer. I started off with a solution to the equation, which I rearranged by timesing by x to the n on both sides. Now I've applied differentiation to it twice, and I'm trying to show that it rearranges into the format that I'm proving. Rather than actually starting with the differential equation and somehow miraculously integrating twice, I don't even know where I would start there. I'm differentiating to show that it solves the differential equation. Okay, we need to get rid of the x to the n term there with the d squared y over dx squared. Remember that d squared y over dx squared needs to be isolated on its own. So if I divide through by x to the n, which is not 0, it can't be 0 because it was in the denominator of the actual solution. Dividing that out, I get d squared y over dx squared. Be careful with this. It's 2n x to the n minus 1. I'll write this step, but then we'll just simplify over x to the n. Of the same base of x, and we subtract the powers. So we get n minus 1 take away n, which is just minus 1. And then we can write that as 1 over x. We can reciprocate it because a negative power is a reciprocal. So getting rid of all that, it actually comes out to be 1 over x, which I'll write underneath there. And if that went too quickly for you, just pause and have a look at what I did there. It's just an algebraic trick. And we do the same thing for the brackets. Now we're dividing by x to the n. So we get n times n minus 1 over x squared. X to the n minus 2 divided by x to the n. And in the other term, it's just plus m squared, because we get rid of the x to the n. All times y equals 0. Now, is that the proof, or do I need to fudge it a little bit more? No, ooh, did I say fudge it? I mean play around with it a little bit more. So we've got 2n over x in front of the dy dx, which is great. N factored n minus 1 over x squared plus m squared. Yes, perfect. So box, smiley face, and it's proven. Catch you in the next video.